Hello, everybody out there in podcast land. This is Mr. Folly, and it looks like this podcast only has 6 slides, so let's hope that although I know these are a little bit longer, we should be able to work it out. What we're going to do in this podcast is look at buffered solution with ice diagrams. We did one of those in class already. A buffer means you have a constant H or OH, meaning the pH won't change. Dissolving in certain pHs, and the removal of ions through precipitation, which we talked about before, but we forget about it so often we're going to do it again. Buffered solution have a constant OH or H value. Calculate the solubility of copper to hydroxide in a solution buffered at pH 8.96. So what we do here is CuOH taken twice. I'll make my pen a little smaller. At least I hope it's smaller. Is in equilibrium with Cu plus 2 hydroxides. That's a dissolving equation. If the pH is buffered at 8.96, that means that POH, because I want hydroxide ions, is 14 minus 8.96, which is 5.04, which means my hydroxide ion concentration is 10 to the negative 5.04. So second log negative second answer is 9.12 e negative 6. So that means my initial concentration of hydroxide ion is 9.12 e negative 6. So calculate the solubility of CuOH taken twice in a pH. Okay, so solubility is the minus x, right? So I start off with sum. 0, and because it's buffered at this pH, that's what I have. So then what I need to do is, this is minus x, this would be plus x, this would be 0. Now the reason why it's 0 is because it's buffered, meaning the pH won't change significantly. At equilibrium, no one really cares, x and 9.12 e negative 6. So my KSP expression is 1.6 e negative 19 equals x times 9.12 e negative 6 squared. So x equals, and that's going to be my molar solubility, so whatever that answer is, 1.6 e negative 19 divided by 9.12 e negative 6 squared is 1.92 e negative 9 molar. And there you go. We did that one in class, but it's good duty. Shouldn't have given it to you in class, but that's all right. How many moles, not molarity, of FeOH taken twice, KSP equals blah, will dissolve in 1 liter of water buffered at pH equals 12.62. So if my pH is 12.62, then POH, squeeze in my O there, equals 1.38. I hope. Yes. So that means OH negative equals 10 to the negative 1.38. That's pretty big. Second log negative 1.38 is 0.0417. So same basic thing, dissolving equation, FeOH taken twice. It's in equilibrium with Fe plus 2 OH negatives, and my hydroxide concentration is 0.0417. Initially I have sum 0. So how many moles will dissolve in 1 liter? So again, I said, oh, moles, not molarity, but it's in 1 liter, so same. Minus x plus 0. Okay, again, because it's buffered. If it doesn't say buffered, then you would still have a plus 2x there. No one cares. You're a solid. X and 0.0417. So 1.8 e negative 15 equals x times 0.0417 squared. So 1.8 e negative 15 divided by the other answer squared gives me 1.036. I'm going to add an extra sig fig e negative 12, which I added that one. It should just be 4. Equals x, which would be moles. This would be moles per liter. Some ions affect solubility just like pH can affect solubility. Ag positive is taken away by Cl, often HCl. Ag positive is taken away by NH3, forming AgNH3 taken twice, 2 positive. Well, you know what I mean. Other ions are affected as well. So remember, other ions are affected as well must be D block elements with excess or excess concentrated and excess or excess concentrated D block metals, by the way. Electron-rich things, which are always NH3, which I'll add that in there, or OH negative. Look at how rich in electrons those are. Okay, and that's what we're looking at. The solubility of silver chloride in water is blank, the solubility of a strong acid at the same temperature. Now, on this one, strong acid means you've got H positive. And it says a strong acid, and it could be any strong acid. So let's just say if it was HCl, then obviously it's going to affect it, but it says a strong acid and doesn't indicate it's HCl. But, okay, so it could be HCl, so let's list our strong acids. HCl, HBr, HI, HNO3, H2SO4, HClO4. So the solubility of AgCl in water. Now, if it's, let's just see, solubility of AgCl in water. So we're looking at the effect of Ag positive ions and Cl negative ions. And if I can form precipitate with any of those, it will increase precipitation with those, increases solubility. So in HCl, will AgCl's solubility increase or decrease? It would decrease because you're increasing the chloride ion, shifting equilibrium to the left. I suppose I should actually write this here. So much for me trying to be lazy. So if I add, probably more color highlighting. If I add Cl, HCl, that means I'm adding it, it'll shift to the left. If I add HBr, does AgBr form a precipitate? Yes, it does. AgBr, remember, AgBr is a solid, so that means it will shift equilibrium to the right, so solubility increases. HI, solubility increases because AgI is a precipitate. HNO3, nitrate, no effect. Ag2SO4, that one I don't know about. I think it's a precipitate, but I'm not sure. I'd have to look that up. HClO4, ClO4 doesn't form precipitate with anything. But the sulfate one I don't know. So it either goes down, it goes up, has no effect, or I don't know. That means the answer cannot be determined. Review: buffered by definition means pH won't change, so don't change the H positive or OH negative in your ice diagram. Many ions react with H or OH, so pH matters. NH3 can remove aluminum and other D block elements, OH2, but usually they do in that. So this is your favorite podcast because it's done in under 8.5 minutes. Toodles.